All right. So welcome everyone to the Fall 2024 eCHT Research Seminar. Today we are happy to have Lennart Meier, who's going to be telling us about duality in equivariant topological modular forms.
Thanks a lot for the invitation to speak here. So my talk will be about duality in equivariant topological modular forms. So in brief, my plan is first to say a little bit about equivariant K-theory, because K-theory is certainly familiar, more familiar to almost everybody, and also easier than topological modular forms. In many ways, the situation is analogous in topological modular forms to K-theory, if you just view it from the right angle, but of course more involved. So I will first talk a little bit about equivariant K-theory and about non-equivariant topological modular forms so that everybody's on the same page. Then I will provide some introduction to equivariant TMF, in particular also focusing on some computational aspects, and I hope I have time at the end to speak about self-duality in equivariant TMF. And I should mention right away, so there's a tremendous intellectual depth in all of this to Jacob Louis. I mean, of course, to many, many more people. For example, Gauss, Hopkins, Miller developed in topological modular forms. But if you know survey of elliptic cohomology from Jacob Louis, some things will sound familiar here. And it's also based on joint work with David Gebner, where we flesh out significant parts, kind of details and significant part of the survey of elliptic cohomology and develop it also further in some directions. And also some parts will be also joint work with Tilman Bauer, with whom I'm working on so-called topological Jacobi forms, which won't feature explicitly, but implicitly in this talk. Okay. So let me first say a little bit about equivariant K-theory, and please interrupt if there are any questions. So equivariant K-theory, well, if I have a finite GCW complex X, then the equivariant K-theory is simply the Grothendieck group of finite dimensional complex G-vector bundles, like the usual definition of K-theory. But in fact, this is also, there's a spectrum representing this. And I just want to say the following. I don't want to define the whole G spectrum, but I want to say one thing. Then we can define a spectrum which I call K of G, Kg of a point, or it might be also called the G fixed points of a equivariant spectrum K, but maybe I don't want to use this notation. There are many ways to define it, but one way to define it would be the following. We look at the category web GC. This is the category of finite dimensional complex G representations. And I should say G is here and everywhere in the talk. It's a compact Lie group. For the moment, you could also restrict to G finite, but certainly would be later very important that we also have arbitrary compact Lie groups. So we can look at the category web GC, finite dimensional complex G representations. We can look at the K-theory of this category. So it has a direct sum, and so there's some K-theory spectrum. So usually this K-theory spectrum will be a connective spectrum. So for example, in the case where G is trivial, we'll get the spectrum little ku, but we want to make it periodic, and so we just invert the bot element, which we can implement by tensoring with capital Ku. Okay, so how does this, we see that pi 0 of Kg of the point is exactly the same as the 0th K-theory of point, namely the representation ring. So which is the same as the direct sum of Z over the complex irreducible G representations additively. Okay. So now you may ask, can we also compute the spectrum Kg of a point? And the answer is yes. It's actually quite simple. Kg of a point is simply the direct sum over complex. It reduces the G representations. Sorry, not over the integers, but over Ku. So it's a free Ku module. So how does one see this? It's just simply that the category where GC decomposes into a product of the categories finite dimensional complex vector spaces, where the product again is indexed by a complex irreducible G representation. And it's not really the product. I wrote this thing. It's like a restricted product, which means we are only allowed to pick finitely many different things. So how does one get this? Well, arbitrary G representation is just the sum of irreducible ones. And how many I take from each irreducible one says how which C to the N I take in this copy of vect C. This is like a short way to say it. But of course, I'm only allowed to do take finitely many, so I have this restricted product, and this restricted product translates into direct sum here. In fact, one can also do the same story for real K theory. It's slightly more interesting. Namely, one gets sum of KOs plus a sum of KUs plus a sum of KSPs, quaternionic K theory, which happens to be the same as a fourfold shift of KO. And the reason is essentially that while every irreducible complex representation has as endomorphisms such the complex numbers by Schur's lemma, for irreducible real representations more complicated, there are three possibilities: the real numbers, the quaternions, or the complex numbers. And I have to count all these three possibilities, and for each irreducible real representation where it's the endomorphisms, the real numbers, you get a KO, or it's a complex number, KU, where it's the quaternions, fourfold shift of K. The details are here not so important, but I want to make two small remarks. First of all, namely, these are dualizable and actually self-dual. KU or KO modules if G is finite. So G finite ensures that there are only finitely many irreducible representations. And well, in general, like if you have a complex Lie group, there would be certainly infinitely many reducible representations. For example, for S1, we have Z many. But for G finite, then the sums are finite and all the summands are self-dual. So also the sum is self-dual. Okay, any questions so far? Okay, seems fine. Okay, then I switch gears and I go from equivariant K theory to topological modular forms. So TMF is a certain E-infinity ring spectrum, which should be seen as some higher form of K theory. Higher corresponds in the chromatic picture specifically the fact that it's height 2 spectrum instead of a height 1 spectrum. And I want to give a very brief sketch of the construction, which is, I'm not sure it's understandable if you haven't seen it, but maybe it can serve at least as a reminder if you have seen it. So it's based on the modular stack of elliptic curves. So this is certain geometric object, algebra geometric object, which parameterizes all possible elliptic curves. And there exists a sheaf of E-infinity ring spectra on the stack. When I take global sections, I get this E-infinity ring spectrum TMF. And in shorthand, this will be written the global sections as gamma. So this is very abstruse, and maybe if you haven't seen it before, and you might also ask if you have seen some flavor of modular forms before, what is the relationship? The thing is that you can see classically also modular forms as functions of, very classically maybe, of functions of isomorphism classes of elliptic curves. If you say your elliptic curve is something like upper half plane C divided by a lattice or something like this in the complex picture. And if you translate into more modern terms, this what you get is that modular forms are global sections of certain line bundles on the modular stack of elliptic curves. And it turns out that these line bundles are exactly the homotopy groups of the sheaf of E-infinity ring spectra. So in some sense, you assemble all these line bundles into one sheaf of E-infinity ring spectra and just mimic what you do with classical modular forms, and then you take global sections and you get topological modular forms. And just one word on how you might actually compute something about this. Well, there is a so-called descent spectral sequence, which has the following signature name that goes from the cohomology of the stack with coefficients in this line bundles I just discussed, and then converges to the homotopy groups of TMF. And well, if you're not so familiar with the stacky language and so on, this might still look very abstruse, but it turns out this is a cohomology of a certain Hopf algebroid, the so-called Weierstrass Hopf algebroid. Which is completely explicit, not only explicit, but has also the advantage over, say, when you Hopf algebroid you see when you're computing the homotopy groups of spheres, that it's finitely presented. So you have a chance actually to compute the whole two term, and you don't only have a chance, but it actually has been done. And before I comment further on this, I should also say it's the same actually in this case as the Adams-Novikov spectral sequence for TMF. So, and the computation here of this spectral sequence, I think, I mean, at least first published reference is due to Tim Bauer, and then there's also on some related spectral sequence, there's Johan Konta's master thesis, and I guess one should also mention Hopkins-Mahowald for computation of the Adams spectral sequence in this context, and so forth. And just to give you a very short flavor of how the spectral sequence is like, I don't want to go into any details, but this is actually not precisely the spectral sequence, but a closely related spectral sequence. And you see it's pretty complicated, but still manageable. One can actually calculate everything, but well, one doesn't do it on a way after. It's actually not easy at all at the point 2. Okay. And maybe I should also comment the homotopy groups are primarily interested at the primes 2 and 3, if you don't have any torsion at higher primes. Okay. So now you might ask, why should one ever consider this topological modular forms? There are actually many different reasons. And maybe the most interesting motivation for most of the listeners here is coming from stable homotopy theory. Namely, these things approximate the sphere spectrum in a certain sense. Because, I mean, the sphere spectrum, we have no chance to compute homotopy groups completely. And not even the E2 term of the corresponding spectral sequences, because the Hopf algebroids or Hopf algebras you're considering are not finitely presented. And so you hope that you write down some finitely presented Hopf algebroid with some corresponding Adams-Novikov spectral sequence, which is as complicated as possible, but still computable, and then you can map into this. And this was happening here. And this has been exploited. I mean, I also write little TMF here as a connective variant, where you can also apply the classical Adams spectral sequence. And just the most basic idea is you just map the sphere into a little TMF. And this has already been exploited in quite crucial manner, I think, in the computation of the stable homotopy groups of spheres. It's explained to an extent in the book of Brunner and Rockness about Adams spectral for TMF, has been employed in the breakthrough paper of papers of Isaacson, Wang, Xu. And then there's a more refined version where you don't just consider this map, but look at the whole TMF Adams resolution for a sphere. And there's, I mean, it has some history, but I mean, there's most famously this paper by Baudry, Behrens, Bhattacharya, Kulva, and Xu employ this. And actually, essentially using some ideas coming from TMF resolutions, TMF is also applied to provide concrete examples of V2 self-maps. A lot of names again, Behrens, Phil, Hopkins, Mahowald, Noachu, and Quigley are the names to name here. So it's important for stable homotopy theory, but actually there are also other things where it's important. Actually in the study of manifolds also has some importance, because there's a so-called Witten genus which goes from string bordism to modular forms. String bordism is some bordism ring, not so important right now what exactly, but it was a insight of Ando, Hopkins, and Resk that this morphism from the string to modular forms factors over the homotopy groups of TMF. And this maybe sound innocent, but this gives a lot of information about the left-hand side, about string bordism, and so about manifolds. And this, for example, has been applied to by Berkeley and Sanger to disprove a certain conjecture, specifically in the dimension 24, by noting that a certain element is not in the image from here, so it cannot be in the image of the Witten genus, and you can translate this into some divisibility results for Pontryagin numbers, which has some geometric consequences. And there's a third motivation, which I'm increasingly interested in. Namely, there's a motivation from physics, namely that TMF is related to some two-dimensional supersymmetric quantum field theories. This often goes under the name of the Stolz-Teichner program. This would be, I cannot really say much more about this for time reasons, or also because I'm not really an expert on this. But I think it's good to know that there is conjectural relationship here, stress conjectural relationship to some physics theory, which has been applied, the ideas in both directions. Okay. So now there are several reasons why we not only want to use this as motivation for TMF, but actually also for equivariant TMF. So one thing is we want to apply it to stable homotopy theory. I mean, there's also equivariant sphere spectrum, and one might hope that a suitable version of equivariant TMF will also allow to study the equivariant sphere. I must say that in this talk, I will only present a theory for periodic equivariant TMF, and it's not understood yet how to produce some connective variant, which would be very important for us actually to apply this to this. And likewise, has been subject of recent study, I want to produce equivariant V2 self-maps in a suitable sense. And I would think that equivariant TMF should be also relevant for this. But also the Witten genus has several reasons why one is interested in equivariant TMF here. One reason is that Lurie actually, I mean, the original construction and Hopkins and Resk of this string orientation of TMF, so this map is very, I should say, very involved. I mean, it's not only difficult, but I think, I mean, it's intricate. And Lurie has sketched in his survey of elliptic cohomology a different approach how to get this, and actually some stronger variants of this using equivariant TMF. This is also a major motivation why I was interested in this. And third point, only briefly commenting this. So often these quantum field theories might have symmetries, and then this should be related to equivariant TMF. So this is a third motivation. Okay. So now I've been already talking about equivariant TMF. I should say something about what this is. And I just want to start with giving like a very, so to speak, unspecific statement. So there's a theorem I will comment in a moment about its history. There's a globally equivariant refinement of TMF, of the spectrum of topological modular forms. So this means that we have, for each compact Lie group, we have a G spectrum TMF, and these are compatible. So this means in particular, and it means a bit more, but it means in particular that if we have a subgroup H, maybe I write it down, that if I restrict TMF G to H, then I get TMF H for subgroup H and G. So as I said, it means more, but it means in particular this. And global equivariant has some advantages, for example, where I can, the restriction maps between fixed points work for arbitrary maps between the compact Lie groups, not just for occlusions. And I should say that the specific statement that one actually gets a global infinity ring spectrum is due to a recent paper by Gebner, Linskens, and Pohl. which is in turn based on my work with David Kepner, which in turn is based on ideas of Jacob Louis, which in turn is based on earlier work in the complex analytic setting of Korenovsky and yeah, many other people. Many people have worked on equivariant elliptic cohomology in the complex analytic setting, like Charles Wesk, Nito Kichlu, Matthew Spong, Dan Berwick-Evans, and Tripathi, and so on, which certainly, I mean, we don't know the exact comparison, as I think, but should be closely related. But of course, like as stable homotopy theorists, we want to have a theory which is not just complex analytic, but where we have also the torsion. And in particular, what you get is you obtain for each GCW complex X a spectrum TMF GX, so that if we take the homotopy groups, then we just obtain the G-equivariant TMF cohomology groups of X. So this part of the picture, we get the G-equivariant cohomology theory for each G. And I should also say that if we just plug in a point, this is for me today the most important G space, we get exactly the same as the fixed points of the spectrum TMFG. So, as you might expect, looking at G-equivariant maps from a point into something should take the fixed points. So this is a general setup, and I said it's a rough form because, I mean, I didn't specify anything about this theory. So you could just take the Borel theory or whatever. It would be, it always exists, but I don't mean that. Okay. So I decided next to give a short overview of known computations. And I should say, before I delve into this, I should say one thing, that because the homotopy groups of TMF are complicated, you don't really want to say, I forget what the homotopy groups of TMF are, and I just do the computation from scratch again about some of this TMFG, I should say TMFG of a point. You don't want to do the computation from scratch. So what you usually want to do, you want to express these fixed points of TMF as explicitly as a TMF module, so that you can input the already known homotopy groups of TMF. Okay, so let me start on this side. Let's just, as a warm-up, take the trivial group, then we just get TMF back again. This should not be surprising. So more interesting, we could take the group, the circle group. In this setting, this is the simplest non-trivial example. And for reasons which I will allude to later, we get just two copies of TMF. TMF plus one fold shift of TMF. And it turns out when you take the D torus, then we get 2 to the D copies of TMF with suitable shifts. So in particular, we know all the homotopy groups because we all know all the homotopy groups of TMF. So for some people might claim the simplest group should not be S1, but should be the cyclic group of order 2. And you can also consider this, and this case has been computed, that what you get is TMF tensor a certain complex, so one copy of the sphere, plus a complex which I've described here by this cell diagram. So I should say a little bit about the history of this thing. So actually, maybe before I say this, I should add kind of maybe one more row to this table, namely that for G abelian, say finite abelian, this is essentially known after completing at a prime, not dividing G. The order of G. I mean, I think I can delete this essentially. Actually, it's known. This result I proved a while ago. So the interesting stuff happens at the group. So, Dexter Chua has computed, has proven this result here at the prime 2, because this is the only interesting point. And then Lin, Tominaga, and Yamashita later found a different argument, which claim is easier for this identification, which actually gives the integral result directly, which gives the uniform description at all points. And I want to give also one more entry in this column, namely SUN. So you might expect that it's more difficult than a torus, but actually what happens is very simple. Namely, you just get TMF itself again. And I will also comment about this later, because I think this should be surprising if you, I mean, yeah, it certainly surprised me when I first saw it. Okay. And also a small comment, I think connected compact Lie groups are approachable in this business. I mean, they're not easy in general, but they're approachable. Finite abelian groups are also approachable. Finite non-abelian groups, at this moment, it's very hard. And I will also comment why later. Are there any questions so far?
Yeah, I'm just curious, why is there a minus sign on the 2 nu? It seems like if you just had 2 nu there, you'd have an isomorphic complex.
Yeah.
Okay.
It's, yeah. So you could also take just 2 nu.
Okay. And is there an analog of C if you go back to like, the K-theoretic case, down a height, is there like an analog of C? Is there some other complex that plays a similar role?
I mean, yeah, I don't really know, because I mean, KC2 is just KO. Sorry, it's just KO plus KO.
Or maybe it's
so
just
you don't
S.
really,
So it's like
yeah,
S. Yeah.
don't really see much. I mean, what's always true, it always like one summand of TMF always splits off, because I mean, this is you can always here it's the same as TMFG. This is the restriction map, but you also have the other restriction map, because you can restrict along arbitrary maps of compact Lie groups, not just inclusions. So one copy of TMF always splits up, and similar for KO. So this copy, but well, I mean, then you have to compute the rest. And for K-theory, it's so degenerate you don't really see much. Okay. More questions? So let me say a little bit what equivariant TMF is, how you actually define the spectra. And case 1 is really G equals U1, so the circle. And there you do following. So you take the universal elliptic curve over the moduli of elliptic curves. So what's the moduli of all elliptic curves? You in particular can say if a universal elliptic curve living over this. And so this actually also carries a sheaf of E-infinity ring spectra. This is due to Louis. And then you say, well, you just take the global sections of this E-infinity ring spectrum. This may seem a bit unmotivated, but there's a lot of motivation why you want to do this coming from K-theory. Because in some sense you can spin the same story in K-theory. We don't look on elliptic curves, but things which look like GM. But this would be like a story of its own. And if you want to know more, I think it's well explained in the survey of elliptic cohomology. But this is what you do. And case 2 is if G is abelian. And you do the following. So you define MG as homomorphisms on the Pontryagin dual of G to E. So this is the Pontryagin dual. So e.g., U1 dual is Z, or Z mod N dual is isomorphic to Z mod N. So it's just HOMS of this group into U1. And it's good that for U1 hat is Z, because HOMS from Z to something is just a something itself. So I get E back. So I will cover the previous case. So, and then there exists also a sheaf of E infinity ring spectra. And then I set TMFG point to be the global sections of this sheaf of E infinity ring spectra. So I should say that now MZ mod N be exactly the N torsion in the universal elliptic curve. Case 3 is G general. And I just say produce MG by Kahn extension, i.e. it's a co-limit of MA for a abelian. Well, and then it becomes tricky where you exactly want to work, but I just say something, it's not so important here right now, what relative spectral schemes. So, as I said, it's not so important what's exactly. What is important here is that you build it from the abelian guys, and that the procedure is pretty mysterious, because you get some kind of gigantic co-limit in schemes, and it's hard to control. And then, but I mean, at the end, then you can again use the same formula. And the tricky part in the non-abelian setting is to understand this thing explicitly. And for some G, we know it, and for some G, we don't. It's a bit like, I mean, if you want to explicitly understand it as a geometric object, which correspond to understanding in the K-theory setting, the representation ring of group. For some groups we do it, for some groups we don't. And this is only hard. So now that we discussed a bit what equivariant TMF is, I want to say a little bit about how you might actually compute it for G abelian. So let's say for G equals U1. Sorry, I think because the sun does weird things, my face is partially in the shadow, but I think it's the most important thing is not my face, but what I write down, I guess. So for G equals U1, the basic idea is the following. So you look at this universal elliptic curve over the model line of elliptic curves. And then you go back to, say, a much simpler setting. So say, let's say you have elliptic curve E over a field. And then it's a classic fact field K. If you want, you can take it algebraically closed. Then if we look at the cohomology of E, coefficients in the structure sheaf, you get K if star equals 0 or 1 and 0 else. And this corresponds to the two copies of so in a little bit more detail, what you do is you can run a relative descent spectral sequence for this morphism P, where you say you want to compute not directly the global sections of this guy, because it's tough. And it must be at least as tough as computing this one, which I find tough. But you want to compute this thing here. And you can use a relative descent spectral sequence where you use the higher derived images of P. And it turns out that essentially you just get 2 copies. So this is essentially what you get from the relative descent spectral sequence. Then you take global sections, and then you get this. And that you get these 2 copies corresponds at the end to that you get just the cohomology of this thing is 2-dimensional. It's a rough picture. And then I want to comment on the case G equals C2. So what Dexter Chua did, essentially he ran this descent spectral sequence for the 2 torsion and the universal elliptic curve. This was hard because we first had to compute the corresponding Hopf algebroid, which was not so easy, and then you had to run descent spectral sequence. And then afterwards, you still need to compare this to this complex C I had. So you had to do these 3 things. And the idea, which I think is quite smart, of Tominaga and Yamashita was use cofiber sequence U1 mod C2 to S0 to the representation sphere of sigma squared, where sigma squared is the representation which sends Z to Z squared. So if this cofiber sequence, so you only have to understand this part here. So you only get from this we get cofiber sequence TMF U1 C2 plus, which is the same as TMF C2. TMF U1 of a point. I guess I have to take reduced here. And then TMF reduced of U1. And it turns out that this thing had been computed by Tilman Bauer and myself. So what we do is we give a cell for each representation. Essentially what we do is for each representation one can put here, we give a cell complex so that what we get here is TMF smash this cell complex. It's in terms of some stunted projective spaces. And they use this to get a cell complex for this thing. And there's sometimes no hard computational work involved. Of course, if you want to know the homotopy groups concretely at the end, you have to compute it. To get the cell complex, you don't have to compute it hard. So before I end, I still want to state my duality theorem. So namely, so maybe before I do this, I go one step back. It's computation. What you might have noticed is that all these TMF models are dualizable, in contrast to the K-theory case. The K-theory case, well, for C2 we got something dualizable, but in this case we got something infinite dimensional. Here it's all dualizable, it's all finite. And this I already proved before together with David Gebner. But actually now one can actually identify the Spanier-Whitehead dual. Namely, it's TMFG. And I guess I should take reduced here. So this is the Lie algebra G. So how does this fit with the earlier thing? So e.g. do it for U1. We get just we get TMF G of S1 because Lie algebra is trivial. So this is sorry. U1, TMF U1 shifted by -1. So I'm taking cohomology. And this is fitting exactly what I had before, because this thing here is TMF plus a 1-fold shift. So when I take the dual, I get a -1-fold shift of this. Furthermore, e.g., if G is finite, then I get just the same thing back again. And this was a theorem before by Jacob Loewy and Jack Davis. So Jacob Loewy proved the general theorem, which states things like this in his tempered ambidexterity paper, Elliptic Cohomology 3. And Jack Davis showed that this actually also applies to equivariant elliptic cohomology. So and note that this is very similar to how the Wirth-Müller isomorphism also looks like in stable equivariant stable homotopy theory, because there also, when you look at the dual of some kind of G spectrum form G mod H plus, then you also see the Lie algebras appearing. And this is one thing which is also used in this proof. And I think I don't really have time to write anything more, but I just want to make a few comments, maybe in words. So one thing is the strong dualizability properties allow you to define a lot of transfers in equivariant TMF. So usually we only have transfers along subgroup inclusions. In K-theory, it has been known for kind of forever that between finite groups, you can also do it, you have transfers for all maps of groups. You can define geometrically in level of vector bundles. But in a sense here, we now have transfers for all maps of compact Lie groups. And what we just do is we use the restriction and then we dualize using this dualizability, this dualizing theorem. And the other thing I should mention is I want to say at least one thing about the proof, namely the crucial thing is that one first proves it in the case of SUN. And not only this statement, but a statement where one is allowed to put an arbitrary X here. And then one is allowed to embed an arbitrary group into SUN and just use the case SUN mod G. This is a strategy. So why is SUN in particular amenable? It turns out that MSUN is a Pn-1 bundle over ML. And this is, one can compute this. This is also a theorem by David Gepner and myself. And this is fairly simple. Pn-1 is a kind of simplest possible scheme you could imagine. So one has very good control on what is happening there. This is in like 3 sentences, the proof strategy. And I think I should end here. Thank you very much.